Hi. So today we are going to cover, we're going to build off what we did in the last video lecture where we discussed vectors in 2 dimensions and how we can break those into components. They have magnitude and direction, all of those things. And we're going to build on that and the fact that position, velocity, and acceleration are all vector quantities. And we're going to look at motion in 2 dimensions. So the general concept of motion in 2 or more dimensions is that you're able to split up complicated many-dimensional problems into simpler one-dimensional problems is sort of what we're aiming to do here. So we're going to use the vector stuff that we learned in the last video and the fact that we can break things into components to do this. And then all the kinematic equations for constant acceleration that we derived earlier in the course, they're still going to be valid for these 2 dimensional problems. So to see how this works, let's consider an acceleration vector, just a general one in 2 dimensions. We have that vector split written in terms of components has some component in the x direction and some component in the y direction. The acceleration can be defined as the derivative of the velocity with respect to time. So writing acceleration that way, we get the acceleration vector is the derivative of the velocity vector with respect to time. And if we break that into components, well, the unit vectors that are describing the directions of those components are constant with time. So those just go through like a constant. And we have the derivative of the x component with respect to time in the x direction plus the derivative of the y component with respect to time in the y direction. Now, if we take these two equations that are equal to each other, they're both ways of writing the acceleration vector, we see that the x components have to be equal and the y components have to be equal. So we have the acceleration in the x component can just be written as the derivative of the x component of velocity with respect to time, and likewise for the y component of acceleration, it can be written as the derivative of the y component of velocity with respect to time. And we can get the same thing if we look at velocity and position, where the velocity in the x direction is just the derivative of that x component of position with respect to time, likewise for the y. What that means is when we look at the kinematic equations for constant acceleration that we derived, and the fact that those still hold for 2 dimensional vectors, we have these equations. The position vector r is equal to the initial position vector plus the initial velocity vector times delta t plus 1/2 the acceleration vector times delta t squared, or the velocity vector is equal to the initial velocity vector plus the acceleration vector times delta t. Those still hold. But it's convenient to, rather than think about them as these complicated equations that have 2 dimensional vectors all in them, if we write them in terms of components. So if we take just the x components of that vector equation, we get this: the x component of position is equal to the initial x position plus the initial velocity in the x direction times delta t plus 1/2 the acceleration in the x direction times delta t squared. You get the same thing for the velocity in the x direction, where all of these terms, the position and the velocity and the acceleration, are the components in the x direction. And we get this analogous thing for the y components, where the y positions, y velocities, and the accelerations in the y direction. So we have these two. What we've done is we've taken one sort of complicated equation that has 2 dimensional vectors in it, and we've split them into two equations that are simpler in the fact that all the terms in them are just 1 dimensional components rather than these vector terms. And what we're essentially doing when we use this to analyze the problems is taking a complicated 2 dimensional problem and simplifying it into two 1 dimensional problems that are related in somehow. So we're going to go through an example in a minute where essentially you'll look at the y direction, and you'll be able to use those equations to solve for some unknown that will then feed into the x component equations and allow you to solve for whatever we need to know. We have these two sets of sort of coupled equations that describe the motion in 2 dimensions. So let's look at an example of that. a soccer ball is kicked with a speed of 22 meters per second at an angle of 17 degrees above the horizontal or the field. How far does the ball travel before it lands? Pretty standard problem, something we'd call projectile motion. The gist or the approach to these problems that's very useful is mirrors exactly what we did in one-dimensional problems. What I like to recommend, draw a picture first to sort of organize how you expect the motion to behave. Use that picture to sort of define the variables you're going to use to describe things in the problem, and then apply our mathematical model, our kinematic equations, to determine the values of all those variables. So let's try this. We have a ball kicked at some angle like that. We'll call that angle theta, and it's 17 degrees, and it's kicked with some initial speed, and it's essentially just going to go at some distance. And if I draw the ground like that, it's going to land somewhere over here, right? So we have all hopefully seen a ball or something be thrown or kicked like that. That's how we expect the ball to travel. Now, the next sort of thing we want to do is sit here and sort of label what we're going to use to describe this problem, right? So remember, we describe motion with position, velocity, and acceleration. So we're going to need variables to sort of label what position, velocity, and acceleration, and that is throughout this problem. The points we're interested in, essentially, are the initial point and the final point of that motion. We could, add points in the middle if we want, but it's not necessary. So what is the position? Well, we have to be careful now. It's a two-dimensional problem, so we're going to need two pieces of information for that, the x component and the y component. So what are we going to call them? Well, x initial, it's a good name for the initial position in x, y subscript I, the initial position in y. Likewise, the velocity has an x component at the start and a y component at the start. So we have our position and our velocities at the start, and we've labeled those variables. I just use subscripts I for initial. There's also, an initial time. We can typically just set that to 0, choose, to start our clocks when the ball is kicked. Way at the end, we were interested at the end, we have the same sort of variables. We're going to want to discuss the final position in x and y directions, as well as the final velocity in the x direction and the final velocity in the y direction, both those components, and that's going to happen at some final time. Now, we learned in one-dimensional motion, and it holds true for two-dimensional motion as well, if there is some object near Earth that's not being touched by anything else, generally we say that that has an acceleration due to gravity that's pointed straight down. So as soon as this ball is kicked, through the entire motion, it experiences a constant acceleration, and that acceleration is straight down. That vector points down at Earth. So that means that acceleration in the x direction is 0. This acceleration vector has no left to right component, whereas the y component is equal to 9.8 meters per second squared, and that's going to be negative. The reason it's negative is because what we're going to do is define our vertical position as y and our horizontal position as direction as x. And if we define up as positive, this acceleration vector that's pointing down is in the negative y direction. So that component's going to be negative 9.8 meters per second. But now we've sort of set up a kind of Rosetta Stone sort of thing where we have, we've listed all the words and concepts we use to describe motion. We have position, velocity, and now we have the accelerations, all listed at the key points in the problem. The positions and velocities, both components at the start, the position, velocity, both components at the end, the time at the start and the end, and the accelerations that describe the entire motion the acceleration along that entire path that this ball is going to be traveling. So we've sort of set up the way to translate our concepts, position, velocity, acceleration, and time, into our mathematical model, where our mathematical sort of formulation of this is going to be those three kinematic equations of constant acceleration that are the final position is equal to the initial position plus the initial velocity in that s direction times delta t plus 1/2 acceleration in that direction times delta t squared. The final velocity in that direction is the initial velocity, in that direction, plus the acceleration times delta t, and v final squared is equal to v initial squared plus 2 as delta s. And I'm using the book's notation here. Sorry, I got a little sloppy and reversed the order of my subscripts in some of these. But essentially, s is sort of in a general direction. So we can replace this s with either x components, or we could replace them with y, and we have all of these equations. So these are sort of the equations as listed in your textbooks and that we've derived earlier in the course. And we have in our figure here sort of a way of translating these into our problem. So we can do that, but some of these things we already know, like our initial position. Well, if we defined this as the origin of our coordinate system as I've drawn, my initial position in x is just 0 meters. Likewise, since I'm starting at the origin, my y position is the same. What about the initial velocity components? Well, this is where we can actually use a bit of what we learned in our last lecture, right? We've been told that initial velocity vector looks like this, and it's at some angle of 17 degrees. Well, what we're looking for is this x component, Vx initial, if this is the initial velocity vector, and the Vy component, Vy initial. And this is a right angle triangle. So we're going to use our trig to figure this out, where the sine and the cosine are opposite over hypotenuse and adjacent over hypotenuse. So that means if I take that hypotenuse, the magnitude of this side, V initial, times cosine of that angle, 17 degrees, I'm going to get Vx initial, right? Because cosine of theta is equal to adjacent over hypotenuse. Vx initial is my adjacent. The hypotenuse is the magnitude of this vector here. So that's going to be 22 meters per second times cosine of 17 degrees is equal to Vx initial. And if I enter that into my calculator, it ends up being 21 meters per second in the x direction. So this is 21 meters per second. And I just got that by breaking this vector into its x component. Likewise, if I do the same thing to figure out the y component, it's just going to be the sine term. And that's going to get me my initial velocity in the y direction. If I enter that, I end up getting 6.43 meters per second. And both of these are positive. These vectors are going, the x component's going to the right, which we've called the positive direction, and the y component's going up, which we've called the positive y direction. So this is 6.43 meters per second. Right? If I look at the final terms, well, I don't know what the final position in x is. That's actually what's asked. The final position in y, I'm landing along this horizontal at the same height I began at. So I know that's 0 meters. And I don't really know anything else about where it lands or when it lands. I don't know how long it's in the air. I don't know how fast it's moving when it hits the ground. And I don't know where it hits the ground. But I do know it hits the ground, which is at 0 meters. So now I can take all of these things the sort of variables I've defined and what I know about them. And these three equations here relate these initial points to the final point. So it's now every one of these equations can be applied here. The question is, which one's going to actually give us the information we want? All of them are right. Not all of them are useful for this particular question. So one of the things I always advise students on is if you choose, when you're first doing these things, just start trying them, start applying them. And if you're applying them right, sometimes you'll get useless pieces of information like 0 equals 0, and that's true. It's not going to help you solve the problem necessarily, but it's not wrong. You might also get one equation with two unknowns. That equation is still true. You just can't solve it yet. So just keep working through these, and as you practice, you'll get more efficient at kind of identifying which ones are going to be useful and go through there. So what I'm going to do is I'm going to start with this first equation here, and I'm going to apply it to the y direction here. So if I translate what that SF equation means is if I change all the F's, S is to y, because I'm talking about the y direction, I have y final is equal to y initial plus vy initial delta t plus 1/2 ay delta t squared. And now it's just a matter of, applying what I know. I know my final y is 0 meters, is equal to my initial y, also 0 meters. My initial velocity in the y direction, which was 6.43 meters per second. My delta t is t final minus t initial, which is 0, so that's just t final, plus 1/2. My acceleration right here, negative 9.8 meters per second squared, and again, t final this time squared. And you can see this is one equation with one unknown. T final is the only thing I don't know. So we should hopefully all be somewhat comfortable with algebra and be able to do this. If we bring it to the one side over, I'm going to get T final is equal to 6.43 meters per second times 2 divided by 9.8 meters per second squared. What I've done here is essentially, because of this negative sign here, I can bring that over to the other side of the equation and then multiply both sides by 2, divide by 9.8, and then divide both sides by t final. You get a lot of canceling. Hopefully you can follow that, but enter that into your calculator and you end up with t final is equal to 1.31 seconds. You can check units here. The meters cancel with the meters. This second cancels with one of those seconds. That second comes up. So I am getting the right units with t final, so that's working out. And if you've ever kicked a soccer ball, that actually seems like a pretty reasonable number for kicking a soccer ball and how long it's going to be in the air. But the point is we've solved for something we didn't know before we did that, how long it's in the air for. But the question asked, how far does the ball travel when it's in the air? So what we're really looking for is this x final. So I need to do more work here. And what I'm going to use is the same equation, but I'm going to apply it to the x direction. So if I do that, that equation, let me switch this up to red, why not, is x final is equal to x initial plus vx initial times delta t plus 1/2 ax delta t squared. And again, all I've done is taken our kinematic equation for constant acceleration and applied it to the x components of this whole problem. And it's now, again, a matter of just plugging in all the values for these variables that I know. X final, I don't know. That's what we're trying to figure out. X initial, 0 meters. V initial in x, we figured that out from our components, is 21 meters per second. Delta t is 1.31 seconds minus 0, so this is just my 1.31 seconds, plus 1/2 ax, but if we go up here, when we were going through this whole thing, we realized there is no acceleration in the x direction. That acceleration is straight up and down, nothing going on in the left or right direction. So this whole term is 0 as well. So now it's pretty straightforward to just take 21 meters per second, multiply it by 1.31 seconds. The units of second cancel, and I end up with 27.6 meters. And I've answered the question, how far does that ball travel before it hits the ground? Right, again, so if we step back a bit and look at what we've done here, is the same sort of strategy we use to solve our one-dimensional problems. It works equally well in 2 dimensions. There just might be sort of more of those steps. The first thing I like to do, draw a picture, some sort of model to help organize your thinking through this. Label, don't think about what we know and what we don't know yet. Just think of how do we describe motion, position, velocity, acceleration, time. We're going to need mathematical variables for all of those things at key points in the problem. So you want initial position, velocity, and time, final position, velocity, and time, the acceleration through that whole problem. And you're going to, since this is a 2-dimensional problem, we're going to need both components for those. So there's going to be an x and a y position, an x and a y velocity, likewise for acceleration. Once you've set up that, we can start thinking about what is known in the problem, and our figure can kind of help us organize that and sort it out. Once that's all done, it's a matter of just applying these equations up here to connect our initial and final positions. And you just sequentially apply them. And typically with 2-dimensional problems in that, you're going to have to use the result. You're going to have to use multiple equations to get the answer that you need. You look in the y direction, like we did here, we looked in the y direction and we figured out how long the ball was in the air. And then we used that to figure out how far the ball went in that amount of time. Anyway, key to this is practice. Keep working on it. Reach out to me if you need assistance or if you're stuck, and we'll get through this.